Done. Okay, we're on, or it will be. And then I'm going to grab, we're going to go over the syllabus first, which seems like a good place to start. We are live, though. That's great. You can see a beach. Isn't that great? Doesn't that look really better than being in class here? Although this is really tiny on my stream. Cancel. Hang on one second here. Let me see if I can fix this. Oh, there we go. That's more like it. Okay. Okay, thanks. Thanks for your patience. And I love technology, but in the process of getting old, I realized that I'm not able to really do it as well for whatever reason. I was so proud of myself back in the day, but now I'm not. I'm not nearly as proud. Okay, here we go. It's just pretty terrible now. Oh, come on. There. Okay, so going over what we have here. This is, as you know, structural equation modeling. Some people talk about something with factor analysis and something with models and something else. And I mentioned it's something that it's not quite measurement, it's not quite statistics, or it's not just measurement, not just statistics. What is it? Structural equation modeling, broadly put, is regression analysis when the things that are in the regression aren't measured perfectly reliably. So if you use surveys, questionnaires, scales, any of that, anything where you had to create a reliability coefficient, but you want to go use it in some type of analysis, other than just forming the scale, the structural equation model is how you do it. How you do it, and actually why you need to do that, is because if you don't, if you put some unreliable things in a regression, that was the part of regression where we sort of just swept it under the rug. Remember, did anyone ever talk about that? What happens if you put things that aren't reliable in regression?
Don't compute them or ignore them.
Yeah, you sort of ignore that they don't have reliability. You put them in, but you know what happens to the regression itself? Anyone ever say that? Okay. Let's imagine this. Let's imagine you're trying to predict someone's success here in their first. Let's say high school graduation, right? Let's predict someone's high school graduation, and you're using, let's say, our state of Kansas 10th grade math test, right? So you have a bunch of students who take this test. It's not perfectly reliable. And you go put it in a regression where you're going to say, did they graduate from high school or not, a couple years later. That regression has a slope, right? So you'd think the higher their score, the more likely they are to graduate high school. Well, if you put something in that regression that's not perfectly reliable, that slope now becomes biased. It becomes inaccurate. Usually it becomes too low. In addition to that, though, it's not just the slope that has a problem. It's the standard error of the slope. Right? It's how much error we think there is. Because the regression itself is treating that high school math score as saying, you know exactly what that score is, just like someone's height or someone's weight. Whereas in reality, you sort of, you know the ballpark of where the true score happens to be. That's what reliability means. It's sort of a fuzzy instrument. Right? So it looks like you have a lot more data than you really do. And so the result of that is, say, the regression comes back and says the error is maybe really small. So it biases the standard error. What happens with standard error, though? We use that to determine whether or not that regression slope is significant, right? And so if you bias the slope, usually it's a little conservative, but if you bias the standard error, it might tell you have a very significant effect when really you don't, right? And oftentimes a type 1 error might happen. So there's this thing going on in science these days. I just got back from a meeting in Washington, D.C., where AERA and NSF organized it. I'm an editor for a journal, and so they brought us in. I edit Journal of Educational Measurement. And the meeting was about open science and open data. And one of the main things that's spurring that is something called the reproducibility crisis in science. I don't know if you've heard of this before. But there's a lot of fields out there where people try to reproduce studies that are published and cannot find the result, cannot reproduce a result. And a lot of those fields don't use structural equation modeling, but do use measurement. And I think part of that, and there's papers that are out that I probably could cite for this, but I won't off the top of my head, Part of that is because they'll use methods that assume all the data are perfectly reliable. But then they use measures that aren't. And sometimes their measures aren't reliable at all. Their reliabilities are like 0.4 or 0.5, which is really, really bad. So I think a lot of what we see in the reproducibility crisis that you see in science is a lack of attention to measurement issues. But then it's sort of the idea, well, what do we do after we measure it? Well, we want to put it in analysis. So structural equation modeling features a part of measurement, which is how do you know what you're measuring truly is there, and how do you quantify reliability for it? Now, you think you may have had that before, but we'll teach you the modern way of doing it in here. It'll also teach you what to do with it afterwards, or better yet, how to go and build that analysis, that regression that you're after simultaneously. And so, again, that's where we're at. The structural equation model is like a regression analysis where you have some of the variables that aren't measured perfectly. Some or all, actually. So that's what structural equation modeling is. Cool? Questions? By the way, stop me with questions. Eventually, I will learn your names, I promise. As soon as I remember mine. It's been one of those weeks. So, back to the syllabus. You can get a hold of my office. You can find me on email, jtemplin@ku.edu. All of our slides are up on my website, jonathantemplin.com, including this syllabus. Were you able, each of you, most of you should have received the email I sent yesterday. Were you able to get to the website and see everything? Okay, that's great. At least I completed that task. My office phone, welcome to find me. I'm in the office a lot more now. So my office is room 614, which is on the other side of the elevator. And my office hours, I'm going to actually not hold in my office. I'm going to hold them in Watson Library, which is the Red Peak building over there, in room 455, which is the Center for Research Methods and Data Analysis office suite. I'm a faculty fellow for them, and I'm supposed to be there one morning a week. And so Fridays, I will be in my office there, and it's a good time to come find me. It's actually not a lot of people around there. I would also say by appointment, but I will note that my schedule these days has become increasingly difficult to find time in. So I would strongly encourage you to try to find me at Watson if need be. But I work great over email. I do reply to emails.
He does.
It may take, the lag might be 24 hours depending on when it comes, but it does happen. I'm slower on the weekend. I have a 2.5-year-old at home, and I like to play with him, so I try to have the work-life balance go on, which is interesting in academics. I'll just admit it. So that is that's how to find me, what to do for it. What we're going to do the course, let me just scroll on down. How you're going to get graded. I hate this part because I want everybody to get an A, first of all. There's 100 total points in class, to keep this simple. I'm borrowing this from my wife, Lisa. 88 points come from homework assignments, of which we'll have 7. 12 points will be in class. I'll have a little quiz. Those quizzes will be about topics that we've talked about in class, and they're not going to be, I'm going to try to keep them big picture. I'm not a great item writer, and these quizzes aren't. Everything that we teach you about measurement, we're not really upholding in our courses. But to that end, the bigger picture topics that come from lecture, I intend them to be kind of also self-assessments. So, how are you doing, what concepts to focus on, and so forth. There'll be 12 points for those. I probably will give, 5 or maybe 6 of them out. But there will also be opportunity for extra credit. In fact, the first homework 0, is essentially going to the online homework system. We have an online homework system for 3 of our homeworks this year, and homework 0. And you'll get to fill out a survey that basically quizzes you on the syllabus. My office is in room, right?
12:55.
That's right. That's right. Well, office hours are. Yeah, that's right. But yeah, basically that's it. How it works. So 100 total points, 7 homeworks, and a couple in-class assessments that I won't. They're not on the schedule, but they'll just be things that if you're following along in class, you should have a good chance of answering. There are no tests. There are no in-class. There are no out-of-class. There's none of that. There's no project, right? But the way I've structured homework is so that you'll be able to, I'd like for you to think of data that you're familiar with. Right? So some of you may not be able to think of data, you may not have your own data, and that's totally cool. I can help you find a data set that hopefully will work for you. But what the homework is going to be like is what we will have an online, the first homework will be something about your data. Basically, go show me some of the original published articles about how this scale was built. You know, what they do for statistics to validate it. I hate that word, nothing's ever totally validated, by the way, but it's to go see it. So trying to tie this to something usable. But then what we'll do is alternate between something online, which is I have a data set that I actually collected a long time ago about people who are gamblers. And so you'll have access to that, and you'll answer questions online about it, and it'll tell you where you're right and wrong, and so it'll kind of give you a guess and check way of working your way through whatever software that you're using. But then follow the next homework after that will be essentially the same type of task, but now on your data, right? So then you'll go, so it'll be like the first one will be do a confirmatory factor analysis on my data, right? And then the second one will be do a confirmatory factor analysis on your data, right? And then sort of iterate between the two so you can see how this works. The goal is, again, to try to take what we're teaching in theory and transfer it into practice for you and what you're doing so you can become proficient at it. So one of the things I didn't mention is what is the software we're using? I will teach the class in R. I will do that because it's free and it seems to be not going away. Right? Everybody hates R to begin with. So if you're new to R, I will have some introduction to it. There's some slides. Also, that's where Lou was also. I'm going to send R questions to, if you have R questions, please contact Lou. That's where I told her, you can be absent, but you have to be present. Think of her as your online help. She'll Skype with you or however connect with you on your laptop, and you can share the screen with her, and she can be like, no, do this or do this, right? So she can literally be looking over your shoulder if need be. And I can too, don't get me wrong, but I think try to give the first pass to her to make her to work with that. I will be doing the grading, by the way. The online homework system and myself will be doing the grading. So Lou's purpose to me is getting you the technical side to be helped with. The other thing, though, is that my wife doesn't do anything in R, but she's built all of this class in M+. So if you are familiar with M+, or if your advisor uses M+, you can use it too, either way. So how many of you have used M+? One. How many of you have used R? Everyone. Okay, awesome. So I'm guessing you're going to use R, but the nice thing about R is that if you're in a spot where your advisor uses M+, M+ is a statistical package that is built by a former professor at UCLA named Bengt Mutane. And he sort of built it away from the university, and he's retired to just run M+. And if you're faculty to buy a license for it, it's almost $1,000, and it's sort of a piece of garbage. Right? But someone in R developed a package named Latent that does almost everything M+ does, certainly for structural equation modeling and almost everything in this class. And so we will see it in Latent, and it's free. So sometimes my wife would say you get what you pay for with R, and some packages are pretty terrible, but this one is actually well done, and I'm very happy with it. The other good thing about it is if you get familiar with it in R, and your advisor says I'm using M+ or whatever else, there's a function it can translate your R code to M+ code, or vice versa. It can take M+ code and translate it to R. So it's pretty cool in that regard. So, but I'm glad you've seen R before. That is part of the reason why we had the prerequisite multivariate for this class, so you at least had a chance to see R. How many of you hate R? It's okay. Just be proud. It's okay. I hated R. I learned R back in 2001, right? I actually learned S+, which was sort of a language that was a proprietary thing from Bell Labs that R is built off of, right? And then when everybody was switching to R back in the early 2000s, I switched to R. I hated it. Oh my goodness, hated it through grad school. I taught in SAS and pretty much SAS the whole way up until I came back to Kansas a couple years ago. And then since Billy teaches and Billy Skorupski teaches in R, I thought this is a time to, and that and the kind of the user curve for it has gone where R is now more used than anybody in SPSS or SAS or any of the languages that you see out there. So it's like, well, now it's time to go there. So, but I have, if you're familiar with R, one of the things that I would recommend, the other thing I do with R is I use a front end, a GUI, a user interface called RStudio. I don't know if you've seen RStudio before. RStudio is terrific. It really makes it easy to, this is the thing that won R for me, because you can write your syntax up here and you can just push a button or two and have it run. You can see the results down in this window, or if you've got the ability to look at markdown results, which is another cool thing that it gives you the chance to do, it'll show up nice. It'll be old-fashioned text over here or cool HTML stuff over here, if however you want it. So, but everybody's seen this. Mostly. That's awesome. So I don't need to tell you. I'm preaching to the choir. Okay. What else? I asked that you do the individual assignments by yourself. Now you can talk to you're welcome to talk to each other. That's what we do in statistics. But when things are for your data, learning how to write about this is a skill I'd like you to learn in this class. And if you're able to do that yourself, I'd like you to do that yourself, right? So you can talk to people, you can talk to me, you can get help, but when it comes down to writing up the results, particularly for the non-online assignments, make that be your own. About late homework, because I like to give feedback quickly, if your homework is late, it gets a 3-point penalty automatically, and that's mainly to get it in on time. What I do with the online homework system is as soon as that deadline hits, the computer is set to display the answers, right? And so if you're late, sure enough, you could game the system and get the answers. Well, I don't think you're going to game the system, don't get me wrong, but basically I'd like for it to make it that way, to make it so it's easy to give you the answers, having a little penalty ensures that. The other part with it is that for the non-online homeworks, I will be grading them, I'll be reading them, or they'll be usually done in some type of word processing software. It doesn't have to be Word, but something that I can edit and comment on. And you'll get a chance to revise them, right? So things that you didn't get correct or things that aren't right, you'll be able to make that work. Now, it's sort of an interesting, doing this revision type of thing is very interesting to me because, there's some of you who are really motivated and write a lot. And I feel like those are the ones I'm really motivated to comment more, right? And there's some of you who, meet the requirements of getting it done, but there's, not a lot of effort put into it, right? So if you want more comments, if you're trying to get more feedback, I would say try to do as best a job as you can. I sort of try to match effort. Now, if I'm off on that, or for whatever reason, if I screw up, that's my fault. But that's sort of my thought with it, right? There is a certain passing threshold. And then there's I really want to learn this threshold, and I will try to help you really learn it if need be. But those homeworks help you write up what your results are, help you go through the results, help you disseminate it. Those are really difficult skills. I don't know, difficult, but they're really important skills, right? You think of all the things you have to do to learn this. You got to learn the math, and you got to learn R, you got to learn Levon, and you sort of forget about, I'm going to write it up because, I could just do that. But no, that's almost like to get that out and well done is really more challenging, I think, than each of the other ones, because everything else is formulaic, and that writing is much less so. So, questions so far? Okay, the grading scale is here. This is, again, based on 100 points. We have readings. Each of the readings are there. Now, my lectures generally draw from the readings, and I would like to say the readings are more for reference. So if you want more information or you want examples of what's going on, readings are very good for that. We only have so much time in lecture to go over this stuff, so I would encourage it. But I will be, the in-class quizzes won't necessarily be on the readings. They'll be more on what we're talking about in class. Okay? So it looks like a lot and may be intimidating, but if you go to lecture or you watch the lecture online and you follow along with the homeworks, or maybe even you try the practice problems. We have examples that we go through. That should be sufficient. But to learn where to cite some of this information from, so you don't cite YouTube or whatever. The readings are good for that. The readings are also good for more information than I can give you in a lecture. So, let's see here. So what we're going to start with, and here's questions, by the way. I'm getting excited. This is a good sign. Like there's still a teacher in me. I feel.
There's no textbook for that class, right?
No required text. No. So nothing to buy, and if you all use R, it's completely free. So you can just. Apart from, I hate, you have to pay tuition. That's the hard part, but nothing extra on top of that for this class.
What was the book you recommended a while back, Bartholomew?
If you're into the statistics side of things, there's a very good book by Bartholomew, Knott, and Mustaki, and I can send you the reference if you send me an email.
If you wouldn't mind, I might still have it somewhere.
Yeah, that book does a great job of the mathematical statistics side of the latent variable models, including structural equation modeling. There's also another very good book that's very technical that I don't have on the list here. That's by David Kaplan, who's also a good C Michael, who's also very good, very technical for it.
Okay.
But what these readings are more built to be accessible by everybody. There's still some technical stuff in it, but it's not pages of matrices.
Right.
And so those of you in the REMS program and who want matrices, I can help you with that, but I probably won't talk about them as much here themselves. So. Let's see. So let's talk about kind of the structure of the course. Today is an introduction, and I have a few slides which we'll get it started, but we'll probably roll those over into next time. Next time is the one shot you get for exploratory factor analysis, because friends don't let friends do EFA. All right. Let's just go there, okay? I'll tell you more about that then, but I'm pretty adamant about that. Anybody had Dr. Poggio? He and I don't see eye to eye on that. And we openly admit it. So this is not, I'm not trying to badmouth him here. This is not it. So I would love to have a debate because I think I have the math. I think math will prove out. As I have this saying that somehow in conversation it came to me this year, oh, math don't care, right? The equations don't care. Like things that are provable don't care what your thoughts are. And there's a way that I can show you that an exploratory factor analysis done the way you should be doing it is equal to a confirmatory factor analysis with constraints on it that are just absolutely crazy and undefendable. And so if I can say that, then math don't care, right? So that's where I'm going with it.
So you want to have a debate because you already know what your argument is.
I know, well, I've got proof. Like, where else in the social sciences can you be like, I proved it? You can't say proof anywhere, right? But you go in the math department, it's like, yeah, QED. Right?
Right. As required.
Yeah. Thank you. But no, EFA, that's the next one, a little bit of principal components. Then we're going to dive into classical test theory. And that's sort of I'm sort of the black sheep of my program. I feel like we have 3 classes that do classical test theory. 725, 822, 921. How many of you have taken one or more of those?
I'm okay.
All of them, right? Are they repetitive?
Kind of.
Yeah.
Yeah, to some extent, yeah.
Yeah. See, I think I got my classical test theory out of one lecture in school. Because classical test theory, you can show the things that you do in classical test theory are equivalent to a confirmatory factor analysis model with certain constraints in place. So you can not only do what you did in those classes that you learned classical test theory on, you can go and show whether or not it fits the data. The model, you're actually implying a model and whether or not it's appropriate for the data itself. You can go a step further than that. So I'm going to talk to you about classical test theory as sort of a frame of reference. The last time I taught SEM, there were students who were really mad they took all those classes. And I'm kind of the part where like we really need to cut that down to maybe one class because ultimately it's sort of maybe you find value in it. I haven't looked at the syllabi. I haven't done an intensive study on it, but my gut feeling is that's a lot of adding things up. Sorry, comments? No.
No, I was just asking her if that was she had taken.
Did you take more than one?
I only took 921.
Okay, so that's good. I'm sorry.
If I would have done it in one lecture, that would have been nice.
Yeah, I think it's an interesting, weird world because there's a lot of people out there, and my colleagues have argued, and I don't want to put words in their mouth, there's probably more of their argument in this, but they've argued that a lot of the world still does classical test theory things, and they're not wrong about that. But if you can show that what you're doing in CFA is equivalent, and then with really restrictive assumptions, right, that data never fit. But if you loosen those assumptions, you go to CFA and it's better. Why use classical test theory? So that's sort of where we're going with this. But you need to have that language to talk to people. And if your committee is going to need to, if they're going to be a bunch of people who understand that, you sort of have to be able to express that to them. But I don't think you need all classical. So, yeah, there are other students who are really angry though. I can't believe I had to take all those classes. Sorry. I'm sort of a pain about it. I'm saying this to you like kind of cocky. But yeah, I can show you that. I can show you that. But yeah, I do that because I'm so angry about it myself. So yes, I should just calm down. Getting worked up, calm down. All right, next is confirmatory factor analysis. So we're going to get into the measurement side of things first. And actually, that's the funny thing about structural equation modeling. Most of what we're going to see is measurement. It's factor analysis, right? So confirmatory factor analysis is when you want to go and see whether or not you have a factor that underlies a certain set of items, right? There's a reason why you build your scale. You're looking at 1 or 2 or 3 or 4 different types of dimensions, different factors. The CFA are the methods to evaluate them, to provide scores for them, to see whether or not the measurement is of quality. And it's going to take a couple weeks, if not longer. But CFA is something where you have your idea about a factor, but you have data that we can claim to be somewhat continuous. Like, what is continuous data? Like my height, my weight, my blood pressure. These are all numbers that have a lot of range and whatnot. A lot of the stuff that we do in measurement or in scales, you give out a Likert type item and there's 6 categories. Is that continuous? You give them 1, 2, 3, 4, 5, 6? Probably not. So CFA is great for the concept, but in practice, when you get to thinking about it, it's really a lot of the data don't meet its assumptions of continuity. So that's where we get into these generalized models, and we start with binary responses. So if you have an item and some person says yes or no to, I agree or I disagree, or even if you have a test item and you score it correct or incorrect, right? They're all binary responses, right? And it's basically factor analysis on binary responses. But that goes by another name, item response theory. Or depending on, in our department, we call that a response theory. If you're familiar with the psychology department, it grew in psychology around the same time, and it was called item factor analysis, which is another same type of weird connection, but they're the same. It's basically, my data aren't quite continuous. Okay, switch from CFA to IRT or IFA. And that's how people end up thinking about it. And that takes a while as well, because it sounds pretty simple. Okay, I'm going to switch over. It's like going from a regular linear regression to a logistic regression, but there are a couple other added features that get thrown in, and I'm going to teach those to you as well. So you're going to see that. We're then going to get into what if your data aren't just categories? What if you have, I don't know, counts, right? Like maybe you're trying to study addiction, and you ask somebody, how many times have you smoked a cigarette today? Or how many drinks have you had, right? These are categorical, but there's no upper end point to them, right? Those might not fit the types of models that we're thinking of. But they don't even have a name, right? They're just, what are we going to do with those, right? It's like factor analysis on counts, right? So, but yeah, you're going to kind of get the sense of repetition with that. Okay, after that, we're going to get into testing whether or not, if you mentioned, I can't remember your name now, but different culture, if you have translations, if you have different cultures, different people, different key groups, whether or not your measurement works the same for each group. Call it in the factor analysis world, we call that measurement invariance. We want to show that if we call a factor, we give it a name, like let's say openness to experience. We want it to be the same meaning, whether or not you're male or female, whether you're from Turkey or the United States, regardless of where you are. And we evaluate that using something called measurement invariance. In the IRT world, that same thing gets another name. It's called differential item function. Right? But again, this is sort of a weird part because I grew up in different disciplines. My degree's in psychology, but I was also in statistics, and I had people in educational psychology. My doctoral committee was statistics, psychology, educational psychology. So it's seeing each of the disciplines, they all have their own jargon for it, but I'm trying to blend them across each of this. So we'll talk about that. We'll also talk about ways of controlling for different designs that you may have incorporated into your study. One of those things, said on here, a method factor. Have you ever built a questionnaire, or you've probably seen questionnaires where they had reversely worded items, right? So, well, sure enough, and what do you do with that when you go and do statistics? You reverse code it. But wouldn't you know, the reverse coding isn't exactly what's happening in the statistics with it, right? It's not exactly one-to-one. And these other methods that show up here are how to use models like this to control for whatever other features you might induce by putting wordings in. So one of the things that you're going to find in the data that we do is that almost every time you do a reverse coded item, it never fits well. Like it fits, the model does not fit it well, and the reason is that reverse coding. It's never as simple as exactly that. The negative, for however reason, the negative, how we'd reverse code it is not an interpretable reverse coding in a person's mind when they're evaluating that item, right? And who knows what that reason is. We all have our own idiosyncratic properties. The method factor tries to come up with an actual factor that's how does this person interpret the reverse coding and control for that on the item as well to help aid it, right? You're not interested in reporting the method factor. You just don't want it interfering with the score that you're going to give somebody. And that's what this happens to do. But there are other parts of factors that might work for that too. You mentioned the clustering example. We could do clustering with the factors as well, and so forth. So kind of branching that out. Then finally at week 13, we start to move into structural equation modeling. We start off with path analysis or path modeling. Mediation analysis shows up here too. A path model, we just use those terms, it often means a simultaneous set of regression equations. Right? You're familiar with one regression equation, but this is multiple all at once, where some of the dependent variables are also predictors of other ones. Right? So you've got this interesting network of linked variables. You're saying this predicts this thing, and this thing predicts something else, and maybe they predict originally. And that's where we get into mediation a little bit. But that serves the basis for what we do, because the structural equation model takes some of those regressions, drawing a path model and path diagram here, but takes some of those and swaps out the predictors or the predicted value, the independent and dependent variables with the factors that we created from the measurement side of the equation. So we do all that, and it's all done, and we all get to sing Kumbaya at the end. And everybody's happy, I hope. Okay. Questions? Sounds like a lot. It's a lot, but it's there's sort of a flow to it. Yes. Sorry. Yeah. Pardon me. Yes.
So about the resources, are you going to provide us with the resources like PDF copies or?
No, I'm not going to. Everything's going to be available on my website. So let me pull that up real quick.
There's the OneDrive readings.
Oh, pardon me. The OneDrive readings. If I sent an email out last night inviting you to that, if you did not receive it, send me an email. It all goes to your KU email address that is registered with on Enroll and Pay. So, and if you can't get into OneDrive, let me know as well. Campus wants us to use it, and I'm full on space and everything else, so it's the one thing I use for classes. When it comes to PDFs and everything, though, I'm not going to put those on OneDrive. Those will be on my website.
Website in YouTube
website.
or the other website?
Yeah, my website, jonathantemplin.com,
Yeah.
will have, this is where I need to, here we go. This measurement instruction equation modeling link, and for each topic you'll be able to find the video link. You can just go to the website, the YouTube. You don't have to You can subscribe to my YouTube channel, like my mom's subscribed to it. This is my first time using YouTube for it, so you can see my mom. But the videos will be posted here, and all the other things will be posted there. But what you'll be able to see is that when you click on some of these titles, that's where everything will populate from. I should put a plus by it to make it obvious. But does that sound cool? Did everybody find that before?
Yes.
Cool. Other questions? Okay. Well, we've got 20 minutes left. Let's start the lecture. No worries. We have a little bit of overlap with a couple things, so we're going to. All right. Here comes the biggest challenge, because usually when I do PowerPoint, it breaks my recorder. So let's see if this breaks. It does not appear to be broken. Is it broken? Okay, I'm assuming the stream's working. No, it actually is working. Hooray! All right. Sorry, when I use Apple's QuickTime and PowerPoint don't like each other because it's Apple and Microsoft, and so when I record off of the other screen, Microsoft won't let me just open the slide view into one screen. It has to pop it into two, and that makes QuickTime very angry, and I don't. Anyway, so I'm very happy this is working. Hooray! Okay, this set of slides is 47 slides. We're not going to get through all of them today, but they're big picture topics and a little bit of history, because nobody wants to know about history, right? If you live long enough, it'll just repeat itself, so you can just live it, right? Say that tongue-in-cheek when I think of the political events these days. That's not a good idea. Okay, so a lot of this, what you see in our class, falls under the heading of something called test theory, which makes it sound really cool, right? It's a theory about tests, a theory of psychological tests and measurements. I use that term because the person I learned this from was a person by the name of Rod McDonald, who's passed away in the recent years. He was a pretty well-known psychometrician and did structural equation modeling and factor analysis. And when I got to grad school, it was the first class I enrolled in, and his book was called Test Theory. And so you'll note over in the psych department, my first job, 2005, 2007, was in psychology. I was a quantitative psychology assistant professor. I relabeled, I don't remember which psych class it is, but I think it's like 890 or something like that. It's now called Test Theory. So that's, if you see that on the books, that's because I was like, hey, wait a minute, that was the class I relabeled. Anyway. It basically is a general collection of methods that we use to evaluate instruments, surveys, questionnaires, whatever you want to call them. We want to operationalize practical problems and provide answers to them. There are actually about 3 branches of measurement you may have heard of. And the first one is classical test theory. Would you like to give us? Classical test theory, I sort of pejoratively call the add stuff up model with my wife, ASU. And if we're not in class, that middle word usually doesn't become stuff. It's usually some 4-letter word. It's ASU model. Basically, this is how you create scores, how you evaluate items, how you quantify reliability. All that starts there. But what we're going to see classical test theory is as a basically one of our confirmatory factor models with a set of restrictive assumptions about how the data perform. Right? So in your 3 classes, for instance, or anybody want to answer this, how many reliability coefficients have you learned over the years? Several, right? Why are there several? It's one quantity.
Because the reason for being several, there's deficiency in each one.
Assumptions, right? So let's start with, you hear of Spearman-Brown? Anybody heard of Spearman-Brown? All right. So Spearman-Brown sounded pretty good. Seems pretty awesome. But then you don't use Spearman-Brown much anymore, right? You got to report what? Cronbach's alpha. Is it really Cronbach, though? Because actually Gutman came up with Cronbach's alpha before Cronbach did. And a lot of what we do, we call it the Gutman-Cronbach alpha. Nobody, they like blows their mind. But no, really, it's like 6 years before, but Cronbach gets all the publicity. Anyway, what happens for both of those is that in Spearman-Brown, does anyone remember why they're different?
They're assuming it's a different kind of error.
Different type of error, right? Spearman-Brown assumes the same type of, essentially, constant error and constant signal across items, whereas, which is called tau equivalent. Excuse me, parallel items. Whereas alpha assumes tau equivalent, which is that the errors may be different for the items, but the signal is all the same. But so when we look at this in this lens, the Cronbach alpha, Cronbach's paper was I think 54, and Spearman-Brown was like 1920-ish, right? We're talking things that are 60 years ago, right? Structural equation modeling, confirmatory factor analysis, in the way that we know it now, really came about in the late 60s. So, sure enough, when we look at that under this lens, we're saying that, okay, each of those is a reliability for when you add up scores of a test under different assumptions, right? So when we get to factor analysis, we may not add up scores. Like if you took, everybody took the GRE, did they add up items to give you your score?
No, they wait.
They use a different method altogether. They use something called maximum likelihood. They try to figure out the most likely score based on your pattern of responses and what the item's properties are. Right? And actually, that's a good way of doing it, but it removes the score from the metric of how many items you took, which is also good because if you remember your GRE, depending on which year you took it, some of you took more items than others, right? Because it was adaptive. And now with the phase adaptive, where they have sort of blocks, I think the same number of everybody takes the same number of items, but it's not on the same metric anymore. So how do you compare scores when you don't get the same items if you're adding them together? Well, if you remove the metric altogether, if you go from saying I'm going to each item is going to count so many points, and you go to this what's the most likely score there is, you can set your own metric. You set the mean, you set the variance, or you use some type of statistical information. You have to essentially provide that metric itself. So that's why your score shows up on the range it does. Depending on what year you took the GRE, of course, they change the range as well. So that's part of what goes on with this. What is a latent trait? The technical title of this class is Latent Trait Measurement and Structural Equation Models, which is a mouthful, but tries to describe everything we're doing. A latent trait is something you can't observe directly. Intelligence, extroversion, depression. So how do you measure something you can't see or can't directly, how do you quantify something you can't directly measure? And that's with a statistical model. So you have these hypotheses. You say basically, let's imagine you have a 5-item scale and you're measuring happiness, which will show up a little bit later. Your hypothesis is those 5 items all measure happiness, right? So you build a model to test that hypothesis, just like you would in a typical hypothesis testing framework. You want to build a hypothesis test about whether or not X predicts Y. You put it in a regression. You have a null hypothesis and an alternative. Here, your hypothesis is that these 5 items measure happiness. And you go and run your model, and you test that hypothesis. And if the hypothesis fails, doesn't fit, they don't measure happiness, or they don't measure at all. There's maybe not one reason. It's just not, the model doesn't work, basically. Yes or no? So that's what the kind of the framework we do. The measurement models are really our tools to provide validity evidence for whether or not what you are measuring is what you think it is. And that's one of the biggest departures we have from classical test theory. How many of you were taught in classical test theory, your reliability is 0.8, you win the end. Right? Reliability depends on model fit of the measurement model. Right? If the model doesn't fit, the reliability is wrong and inflated. Right? So what we're going to learn in this class is that reliability is a summary statistic. It's a consequence of the model. This is one of the things that I really hate about the classical test theory classes. It's like, oh, get reliability, you're good. You're not actually testing whether or not the model fits the data. Question?
Just like so why do many researchers still use these reliability indices if CFA has been around since the 1960s, even in the score? It might be a critical question.
No, it's good. It's a good question. And that's the question, it's the reason why I have a job, first of all. The reason for it typically is the lack of training. So it's been around in research since the 1960s. And typically in statistics, what you'll see is some statistic hits in theory, and then it gets built into software. So in the 1960s, the theory for it came. In the 1970s, Lizerl, ever heard of the package Lizerl? It was like Carl Euroscod was the person who built that package, right? So then it's in software, and people are starting to use it and see its value in research. And then eventually people start to teach it. Simultaneous to CFA hitting software and being taught, though, there is a trend in psychology, and this is where a lot of this work had came up, was that a lot of psych departments were getting rid of their quantitative programs. Our psych department here might be getting rid of it. They have one professor left. And they're doing a search this year for someone who's not necessarily quant, but maybe has quant skills. Right? So it's its own thing. So there's been this lack of transfer. In education, you do see bigger measurement groups, but often they're focused on item response theory, right? Educational measurement. And so you don't see CFA taught in education very frequently. In fact, before I came back to Kansas 3 years ago, we hadn't taught this course, 906, since 2006, I think, or 2007. So it's been this long chunk of time. So I think part of the issue was this came along when everybody thought they had known everything, and so they don't need to learn anything else. And part of the reason is we just don't have the apparatus that's good enough to train it. But trying to train it and make it work, it's a good question. I will tell you though, the other part is that people are really entrenched. They love the way it does because classical test theory never tells them they're wrong. We're going to see in the next lecture, actually next week, if your items correlate at a value of, let's imagine you have all your items correlated, right? Let's imagine 30 items. What's the lowest correlation you could have on average between your items and still get a reliability of 0.8? And this is alpha, by the way. It's 0.1, right? Would you feel confident in your items correlating at 0.1 and thinking they're a scale? No, but that's how reliability works. The more items you have, even if it's barely correlated, better reliability works. So classical test theory works. I built my scale. I had 30 items. People took more time. Good enough. Move on, right? So I think there's a part saying that if you come in with a more interesting model that people don't understand the math of because they're not trained in mathematics, and it tells you that your work is wrong, you're not going to believe it, right? Because look, you've published all these papers. You've received funding. You keep getting funding. Why should I change my model, right? But that really is math. Math don't care, right? It's the same. So anyway, that's my thought of it. Good question, though. I fight this battle with my colleagues in my program. Some, right? Some of us have seen the light, and some of us haven't. So it's still an ongoing fight, unfortunately.
So I have a question.
Yeah.
So there are some assumptions, and like meeting those assumptions will give you approximately an accurate index. If we use alpha, for example, like one of the assumptions, the uncorrelated error between the items.
Right.
So what about if the instrument itself, the data, meet the assumptions of that?
That's fine. Yeah, it works. But how do you know it meets the assumptions?
I would test for of course, I use confirmatory factor analysis.
Ah,
I can't confirm that.
That's right. Yes.
This is it is meeting the assumptions.
Agreed. If you do that, you're in much better shape. But if you didn't know CFA, and all you knew was reliability at 0.8, you don't have a way of testing those assumptions.
Yeah, I agree with you.
Absolutely. So what you'll see in CFA is a lot of people will do a CFA to test it. Exactly what you're saying. Yeah. And they will say, okay, great. Now I'm going to go back to classical test theory to provide reliability or to provide a score. And for the most part, if you meet the assumptions of CFA, most of the time, that will be approximately the same. Not all the time, but most of the time. So, yes. But yeah, it's a tough part. It's the part that CFA does, in part goes and says, I'm going to check the assumptions of classical test theory. But did you hear about CFA in your 921? No. Did you hear about CFA at any?
921?
Yeah. You
Yes,
did?
yes,
Oh, you did? Okay,
yes.
that's good. A lot?
No,
No.
It's like
Like a week or two.
we
almost lost.
we have an overview. We had an overview.
Okay. Not in 822? Not in 725?
822 as well.
Oh,
But
did.
it was the same instructor.
Oh, okay. Okay. Billy?
Yes.
Ah, gotcha. Yeah. And I think who also depends on if he teaches 921, it shows up there too.
Yeah.
No, it's true. If you have that worldview. So for me, my worldview was like in looking at the things you teach that are classical test theory based. Like, why would you even start there? Like, I came into the world and I never took a class in classical test theory. I just got this. Oh, no, I don't understand. So I think it's an interesting world. If you do believe, if you took classical test theory and you learned CFA while you're doing that, then yes, you're fine most of the time. But not all the time. Other questions? How close are we? Got a couple minutes. I'm going to try to get a couple more. Okay. What are the differences among these models? There are a bunch of models that are out there. Let me see if I get this right. What is the name of the trait? In classical test theory, we often called it the true score, like that one. How can it be false? It's true. In confirmatory factor analysis, or anything that's factor analysis, it's the factor score. Have you been warned that factor scores are evil, by the way? Has anyone ever learned that? Okay, good. Good. There are other places on the planet that were taught in the 1970s that factor scores are the devil. And then they turn around and use factor scores like from your GRE to whether or not to see whether you should get into grad school. So anyway, it's just odd. They don't understand this. But yes, factor scores are not evil. They're our friends. But in item response theory, we often call this thing theta. Whatever. So anyway, there's lots of different labels. You can see there's different fields that sort of start at each of these things. But the big difference in the approach is that in classical test theory, the unit of analysis is the test, right? Your score. Whereas in item response theory, confirmatory factor analysis, and a lot of the other latent trait methods that are out there, the unit of the analysis is the item, right? So in classical test theory, if you want to make a better instrument, you make the test longer. In each of these other methods, to make a better factor, you need better items, right? It doesn't matter which these items are. In classical test theory, it doesn't necessarily matter which items they are as long as they're correlated. In CFA or an IRT, you really have to pay attention to those items are part of the factor that you're trying to build, which is what you try to do when you build the test anyway. And we mentioned this before. If you've got continuous responses or plausibly continuous, that's where CFA matters. Categorical responses is where you get item response theory or item factor analysis. But there's a bunch of other ways to it too. Pretty much anything that has a statistical distribution can be used in the same framework. They just don't all have names like CFA or IRT. The other terms, again, structural equation modeling is our regression, simultaneous bunch of regression equations where some of those variables are not measured directly. They're factors. Path analysis is usually used for regression, simultaneous regressions, where all the variables are not factors. Mediation is regression with better marketing. Do you want to do mediation? Anyone advisor is concerned about that? Okay. Oh yeah? Okay, good. I'll talk about that. So mediation is, you're saying that there's an outcome variable, and you're saying that the first variable has both a direct effect on the outcome and maybe an indirect effect through the process of a mediating variable. But now but what it really boils down to is, in a very simple mediation model, there's two regression equations, right? One of the predictor variable predicting the mediator, and one of the predictor variable and the mediator predicting the outcome itself. And so that, depending on whether or not all those variables are observed, if they're all observed, it fall under the heading path analysis. And if one or more of those aren't all observed, we'd probably call that a structural equation model. So you have this type of work for it. Moderation. Anyone do moderation? There's a grant agency for education called Institute of Education Sciences, and they put in their grant call mediation and moderation. We want to talk. You have to talk about mediation and moderation, like in the same sentence. It's like mediation is one way that variables may work to predict an outcome. Moderation is interactions. Like if you learn interaction terms in regression or ANOVA, it's moderation, right? Then they have people who go along and say, I want moderated mediation, right? It's mediation with somewhere where there's some interaction involved, or mediated moderation, right? Right? It's all sorts of stuff that make you pull your head out. But pull your hair out, but it tries to fit on to some research hypotheses that people have built. It may not fit for everything that you do, and that's where my problem with IES was it seemed like you had to have a study that had moderation and mediation in it, and people going, yeah.
Communication studies is kind of obsessed with mediation and moderation.
Oh, definitely.
But then confuses the two.
And that's one of the funny things about it. So yes, we will try to, when we get to path analysis, we will be very clear about which is which. Yes.
Is mediation related? Maybe this is how it was. Is mediation related to the partial and semi-partial aspect in the regression?
There's parts of it that are, but it's more what you're trying to quantify in mediation is not only the direct effect, which is what essentially the slope that one variable would have in a regression. You're also trying to figure out whether or not there's an indirect effect. So when X predicts the mediator, and then the mediator predicts Y, you're seeing the strength of relationship of the mediator for Y and the strength of the relationship of X on the mediator and pooling those to talk about the indirect effect. So involved in the indirect effect, you could say there's a partial coefficient because both of those are predicting Y, but it's harder to pin down exactly. But at that note, I'm out of time. I really hate running over, so I will stop here. If you have questions, hang out after class a little bit. We can talk then. But otherwise, I'm hopefully going to make this available on YouTube. You'll see a link on our class page, or again, you can subscribe to the YouTube channel, and it should tell you when I post it.
I have a question about factors more.
Let's talk after class. Okay. Thank you, everybody.